and our estimators for how the data is distributed become worse and worse. And so there is an optimal level that one should stop in order to get such estimators. So you can develop the whole theory here, and I'm not going to tell you the details because I'm out of time. I'm just going to show you one example where we use this. Well, maybe two. One is we can produce handwritten digits. So we can learn, oops, one too many, two too many. All right, I'm going to go slower now. We don't want to look at that? Okay. So we can produce handwritten digits. Sorry.
It's an anomaly under
That's right. So these are super high resolution images, and that's why lots of points. So not these, the ones in the next slide. So we can create digits. So we look at some digits in the database. These are points in 800 dimensions, and we output a probability measure in 800 dimension. We draw from it, we get pictures. These are just pictures of sevens, for example. Before I showed you pictures of more digits. And we say, are we doing well or not? Well, we should be very careful. I don't have the time to do that. If you have questions, please ask them later on. But we compare with other algorithms. For example, let's just compute the SVD of the data. I cannot do estimation in 800 dimensions. I could reduce the dimension by SVD and do some probability density estimation there. These are much worse. I can show them to you on my screen, but they look much worse. Or you can use some fancy Bayesian algorithm that does that. And if you look at these, they look better than mine. And I was shocked because I couldn't believe that it was working. And there is no guarantee on this algorithm. But in fact, if you go and check very carefully, and this is what this is supposed to represent, these digits are undistinguishable from the digits in the training set. So this algorithm is actually just reproducing things which are essentially in the training set. While I could go and measure and show you that the digits that our construction produces are significantly different from the ones in the training set. So these are truly new digits, like if a person had written them. We use this for anomaly detection. This is the, and instead of going through this, let me just show you a practical application. So we have hyperspectral movies. So they have cameras that take a hyperspectral image of with about 300,000 pixels and 128 spectral bands, and they take one such picture every 8 seconds. So it's a movie, and each frame is a 3D data cube, X, Y spectrum. So it's about 30,000. Well, I don't know, but it's a lot of numbers every 8 seconds coming in. All right, and you can think that every frame, every hyperspectral cube, is a point cloud with about 300,000 pixels in 128 dimensions. Now, they're staring at a desert, and then at an unknown location, at an unknown time, some barrels with gas, which is not visible, but it's visible in the near infrared, is released. And we would like to detect that event. And so this is the point cloud of spectra projected down in the top 3 principal components as a function of time. So the data is jiggling around. Every snapshot here is a projection of a frame in the movie. And the anomaly is actually what is blue here. It's somehow hidden in there, and it's happening. What we do is we use the first frame of the movie to learn a distribution in 129 dimensions of normal spectra, of desert spectra. And then, whenever a new frame comes in, we ask which spectra fit our probability measure, are likely according to our probability measure, and which spectra are not likely. The ones that are not likely, we flag as being anomalies. And so, in this representation, we have a 2D image, and the color is the probability of seeing what we're seeing, and the dark blue, the darkest blue, is what it's very unlikely to be something belonging to the desert or the mountains or the sky. And you can threshold that, and you will see, the chemical plume being released. So this is a task where I think you do have to talk about probability distributions on the coefficients. Having a dictionary or a compression is not enough. There are dependencies which are crucial. Think about the problem of writing a handwritten digit in a weighted basis. I don't know anybody who can do that. Okay? There are so many correlations between the weighted coefficients, you would have to learn those. It's very complicated. This is one way in which we're trying to attack this type of problems. Okay, so I'm gonna stop here. These are some of the features of the algorithms that I wasn't able to tell you about. And this is our new group at Duke that I already mentioned yesterday, looking at large data. And this is Nate and Stas, collaborators on this project on dictionary learning. And this is Bill and Guang Liang, with whom we did the first geometric wavelet construction. Thank you. Please ask me any questions you might want.
Okay, are there any questions now?
Yes?
Question. When you split the set, you take the difference between the estimation and the
Yes.
But you actually assume the error.
Yes. So
When you take the difference, you assume the error. And if the higher moments of the error behaves not very good or just do not exist, the error will increase very bad manner. Some comment on this?
yes.
All the examples you give, the error is limited. So if I write a digit,
Yes.
the error is the size of it.
That's right. Very good. Yes. Yes. So in the context of the theorem, all these errors are always bounded. In fact, we can bound them even in L infinity for all the moments. So there is no problem with the errors blowing up, and that essentially follows from this assumption that the data is in the tube around the manifold, and the fact that the probability measure is absolutely continuous with respect to the bag. There are easy generalization and harder generalization. So you could say, well, instead of a tube, maybe I have some decay of the manifold. Now, if it's Gaussian, nothing will change. If it has fat tails, then a lot of things will change. And some of these errors, for example, will become much larger with much larger probability. And that's a case that we have not done. It would not be a trivial generalization of our analysis. And it would be interesting to look at, in my opinion. Yeah.
Any other quick question?
Yes. When you do the multi-resolution analysis, how strongly does this result depend on the distance you choose? I mean, if for example you don't want to choose the L2 distance, but you want to choose the solver distance, you have some requirements. I presume some sort of doubling property is needed in order to make sure that you are really shrink.
Yes. So okay. So because of the assumptions of the probability measure, particularly that it's absolutely continuous with nicely bounded constant with respect to the bag, it's doubling. So the measure is doubling with a doubling constant, which depends on the intrinsic dimension, actually. And now, you could change the metric, and the tree construction will go through. The properties for the CJKs will stay nice, and no problem. So that part of the construction will go through. Then there is the part of the construction when we do this lower rank approximation locally. Well, there we're doing PCA. So it's a very Euclidean thing and a very L2 thing to do. And so if you change your metric, you would have to ask, what should I do instead of PCA? Right? And so we did. So that's the work that we're doing on the metric version of GMRA, where we replace the PCA step with a step where we say, we look at our metric space locally. We ask, how Euclidean does it look like? Let's try to embed it in Euclidean space, just that piece of the metric space, and let's do PCA there. Now, this will fail at large scale, because if the space was really non-Euclidean, you're not going to be able to embed it in Euclidean space with small distortion. But as you go down to finer scales, depending on the fine properties of the metric, you might be able to embed it in Euclidean space and do the analysis. And then this scheme works under assumptions that the metric sort of becomes more and more Euclidean as you look at finer scales, and works in the sense that it gives you a dictionary, gives you a transform, and it gives you an encoding for the data. For truly non-Euclidean matrix, I think it's open.
Any other question? I do have one.
your theorem, the theorem you have stated today, essentially says that if the probability measure is something like concentrated on a low-dimensional manifold plus some small noise,
Say,
then
yes.
you can get a dictionary as good as this one.
Yes.
But the key, I mean, from a practical viewpoint, the key is to obtain d, the small d, which is something we learned yesterday how to do.
For example, somebody else might use their own method for it. Yes.
I mean, this theorem just says, I can do this with this kind of probability distribution.
That's right.
This is the content of this
Correct.
theorem.
So it says, if the data satisfies these geometric assumptions, then we can do dictionary learning really well. If it does not, no claim.
The proof or the construction essentially follows these lines. You first group data in small subsets, and then you aggregate using PSA in this particular. And then you can rewrite the coordinates or the new features by this difference.
Yes. In fact, I mean, in the theorem, we don't even have to use the differences. We might just use the planes at a well-chosen scale.
Okay.
You can do that. You can use the difference. It turns out that the sparsity in the theorem is d because we're using these d-dimensional planes. They are fine, so that's the d plus 1. If you use the differences, you get small d times the number of different. The differences are also small d-dimensional, and they're at most log of 1 over epsilon of them, so it's comparable.
Could one group data in a different way and use different aggregation procedures in the different subsets of data? For example, using trees, we keep the dyadic cubes and use, let's say, the distance to clusters in each of these nodes. Have you tried this, or have you tried these other methods for grouping? Or the idea here is that PSA and dyadic cubes are the best suite for analysis?
Okay, so there are many possibilities here, right? How do you divide things? How do you do the dimension reduction? Do you then go and prune and use something else after the fact and so on? And so we try to constrain ourselves to situations where we can compute things fast. So this is a situation where we have this cover tree algorithm that allows to compute the tree rapidly and in an online fashion. So if new data comes in, we can add it to the tree very cheaply. Very few other algorithms can do that. But also, we wanted to prove something. And now, the big problem here when you try to prove something is that the CJKs, the pieces that you get, are random. You saw the data, you ran your clustering algorithm, hierarchical clustering algorithm, and you get these pieces which are random. And I know very few hierarchical clustering algorithms that can tell you anything, even under the geometric assumptions of the data that we have, about how these pieces are going to look like. And so for cover trees, we can do that with extremely high probability pretty down the tree. And we like that. And that's why when I tell this story, I stick with cover trees, why we coded it in that way. It could be that by gluing and redoing something different, you get even smaller dictionaries. I think that that's not true in the worst case scenario, but I think that in the sense that I can play with my manifold so that that doesn't happen. But in practice, it could be that in many cases, by gluing and post-processing, you do get smaller dictionaries. In the original geometric web paper, we suggest many ways of redoing that pruning and cutting and so on. There are no proofs, but oftentimes we do get better results. And I think that there is a lot of space for exploring those possibilities. But once you start asking, you know, I want to be able to prove something, and I want a fast algorithm, and I want it to be online, the space of possibilities suddenly becomes pretty small. Yeah.
Thank you very much.
Thank you.